Hello, my name is Jonah Mervitz, and this is Physics 2211, Lab 1, Constant Velocity. So firstly, I'll talk about an introduction, then models, experiment, code, discussion, and finally the conclusion. Introduction. So, purposes of the lab. There's multiple purposes of this lab. First one is to observe an object moving with constant velocity, meaning no forces or change of direction. Another one is to compare a real-life scenario to a computational model online, which would help us understand the fundamentals of classical mechanics. Fundamental physics principles. So firstly, Newton's first law, then Newton's second law, and the idea of constant velocity. So Newton's first law states that an object will stay at rest unless acted on by another force, and an object will stay in motion unless acted on by another force. These are both specifics of the second law, which states that force applied on an object is equal to an object's mass times its acceleration. So force is required to accelerate an object to change its velocity. The idea of constant velocity states that with no forces acting on an object, the object will not accelerate and will continue with a constant velocity unless it ever encounters a force. Models. First model we used was the average velocity formula, which we used to calculate the starting velocity for the computational model. The second one is the position update formula, which would graph position updates for as a function of time that we could use to calculate a position versus time graph. The last one shows that with no net forces acting on an object, everything to the right of the initial velocity cancels out, and Vf equals Vi, which means velocity is conserved and constant. Overview of results. So this is a graph obtained that shows the experimental values that we obtained and the ideal conditions from the code. Both graphs are very similar and very close to linear, which shows that the constant velocity is that velocity is constant and net force is 0. Experiment. So the object/system was a trolley. The surroundings are friction from the track and air resistance that we didn't account for. The procedure that we used was to record a video of an object traveling with constant speed, a trolley. We uploaded it to Tracker. We used Tracker features to track the motion and obtain graphical results. Then we imported it into Excel and compared the results that we obtained from Tracker to our computational model results. So our initial conditions for the experiment, we used the initial position and the average velocity formula with our initial time and a delta t, and change in position to calculate our initial velocity to be 0.15689 meters per second. Computational model. So key ideas behind our computational model: the net force equals 0, line 56. Constant velocity, as stated before. The momentum principle on line 60, updating the position for every delta t. Lines 67, 68. Plotting the two curves, the position versus time graph and a velocity versus time graph, and then lines 35, 36, the initial position and velocities that we calculated 2 slides before, and lines 39 and 40 shows that time starts at 0 and our time size of each time step is 0.33 seconds. Discussion. So under ideal conditions, we calculated a graph of y equals 0.15689x plus 0.00303, and with our real forces from our experiment, we calculated a graph of y equals 0.187579x minus 0.006. As I stated before, these two results were very, very similar. However, there were some possible sources of error, which would be reflected in the r-squared values. Under ideal conditions, we got an r-squared value of 1, and with real forces, we got an r-squared value of 0.9996. And these can be accounted for human error from the video and Tracker, and unexpected external forces like friction, air resistance that we didn't account for. Further questions. How would the results change if the axes were flipped? So if the axes were flipped, the directions would be flipped. If every positive x value would become negative x value and vice versa, and the slope/velocity would switch signs, and the position would switch signs. Which forces are added together? So every force that's being applied on the trolley is being added together, but because the velocity is constant, as seen from our results, the sum of all the forces is almost 0 in our experiment. However, in the ideal situation, the sum of all forces is exactly equal to 0. Conclusion. So, Our results show that Newton's second law is supported. Our actual and expected results were very similar, and because we got linear graphs from both, we can assume constant velocity with when there's no net forces acting on an object. Thank you.